Oh yeah, today we're going to be talking about section 20, right? So this is going to like hypothesis testing, A/B testing, basically all a statistical test. It's very similar to like it's kind of an extension to what we started in last month in mod one. So just some more details. So first of all, I'm going to go ahead and well, I'll go ahead and share my screen and always have a little race with myself, being how fast can we get this done? Okay. So cool. So you guys can all see my screen now. Awesome. All right. So I've been keep putting in what's it called? All of like the stuff I go over instead of using Colab, just because I realized it was just well, I'm basically doing a notebook and then uploading to Git Colab anyway. I'm like, well, I'll just put it in GitHub every time. So I'll send it through. So this is specific for today. I try to order it by like subject versus like sections because in my mind I think that makes more sense. Because you might want to say, oh, in specific part of the section, this part of it. So anyway, I sent you guys through the Zoom chat. You can check that out. So this kind of goes through this first one. Oops. So the first thing we're going to talk about really is like experimental design. And that's really like when we're doing, an experiment. For the most part in data science, we tend not to be the ones who design how to collect the data. We might be working with a company to say, hey, it would be really like a company might say, like, or your business or whoever you're working with might say, hey, we really would like this information. How would we go about collecting it? And you might say some of the things and stuff as a data scientist. But for the most part, we might be the ones who are more like analyzing that data. We're kind of figuring out, what's it called? Like, what's like how to get like once we have the data, or if we're getting data from somewhere, we're usually not the one designing the survey and stuff like that. So just kind of be aware of it. But it should, just because we're getting data from somewhere else doesn't mean we shouldn't be aware of the actual experimental design, how that data was collected. That's actually a really key point of getting data, because your data, it will say everything that like it'll have all the information, but if it was collected in a different way, it can be really, really, obviously bad. Like it could be biased in some way. One famous example, I think it was done in the UK. I could be wrong, but I believe it was a survey that was basically given, and it was asking, what was it? I'm gonna butcher, so take this with like this is me paraphrasing, but it was asking a survey of like people who are Muslim, say are you Muslim, and then it was saying, do you support jihad? And the thing is that when the survey results came out, it was like, 95% of Muslims, I'm making stuff up, but it's like a very high number, support jihad, and stuff like that. And they were saying, like what this means. And in the survey though, if you actually look at it, first of all, that question's like, do you support jihad was in there. And a majority of people did, say they support, but then they also asked before, say, how do you define jihad? And it was defined, he's like, is it violent holy war? Is it basically like different definitions? And those results of what people chose weren't released. It was just the second part. And it was one of those things like, wait a second, like how many people actually are saying this? Like, are you trying to basically put on, people presenting the data, were they trying to present a narrative that wasn't, really truthful or representative of what the world actually looks like? And so those are the kind of things like, it was true, 95% or whatever the percentage was, said they supported jihad, but what that actually means might be something different depending on how the survey was actually taken. And then also, in this case, it was also an internet survey, which means anyone could answer it. So who even knows, who's actually answering and stuff like that. And some of that details weren't actually released. Fun fact that actually, not trying to be political, but kind of give the idea of this bias, Kellyanne Conway is the one who actually was in charge of that survey. So this is where the things where you come through is like, just because, what's it called? Knowing where the source of things are, it doesn't necessarily mean that you can immediately write it off, but being aware of like, maybe intentions, whether or not they were purposeful or not. For example, if you are getting information about how good cereal is from a cereal company and their research, and they say, cereal's great, it's not necessarily that it's wrong or that they are purposely trying to lie, but maybe the people who work for the cereal company might not want, negative results. Like maybe they feel pressured to have positive results in that sense. So it's always coming in with a grain of salt saying, okay, I have data and I can do analysis on this data, but it's not in a vacuum. You have to see what the concept is. And that's really comes down with the whole scientific method, experimental design. So something to always consider. And so again, that's why we always think about like where this data is coming from. So it's actually funny is that I used to be, I think I've mentioned this before, I used to be a science lab teacher for like a middle school. And we would do basically science fair projects, and we would talk about the scientific method. And the funny thing is pretty much scientific method is pretty much what we're doing too. You know, we are data scientists, right? So if you don't remember scientific method, the main parts are basically you come up with a question or observation. Note that this isn't like a firm, like this is the scientific method. It's much fuzzier than that, but this is the general like idea of what the scientific method looks like. Basically, you come up with a question, maybe it's an observation that you noticed or something that you want to answer, right? And then the first thing you do is you see what information is already there. What kind of background knowledge? Do the research. You figure out what's already been done before. So, you know, maybe you find that this question is already answered. So maybe you want to confirm that answer, or maybe you use that answer to ask them something, a deeper question. Okay, so that's kind of your research going through. Once you have that, that's when you actually start thinking about the actual design of your experiment. And for us, the design of our experiment is really saying what kind of data are we analyzing and what does that look like? So that comes with basically determining our hypothesis. In this case, we'll usually do statistical testing. So usually that's your null hypothesis and your alternative hypothesis. And those are always at odds with each other. They're always the opposite. Essentially, you either reject the null hypothesis or you fail to reject the null hypothesis. And the idea is that we're trying to get rid of, ideally what we want to try to essentially do is reject our null hypothesis in favor of the alternative hypothesis. But our null hypothesis always is kind of like if nothing else changed, okay, or null, right? So that leads us to the actual experiment. And this is where like sometimes we don't necessarily have the control of how the data is actually collected, but we should actually be aware of like, okay, how is this data collected? Where did this come from? What kind of things do we need to think about and stuff like that, okay? But this also comes down to the fact when you actually do your testing, when you do your analysis, we'll see that we have to decide on certain factors such as our confidence level, our confidence, so our alpha, our p-value, saying what is significant for us. Sometimes alpha values, you know, we'll say, oh, 0.05, but maybe we need it to be lower, maybe we even need to be higher. But there's drawbacks on those parts of saying when you make it lower or higher. There's also how big is the sample size? Do we need a larger sample size to actually give this information? Do we have enough samples to actually achieve that, you know, alpha, our significance, or, you know, and later we'll talk about beta, basically saying how many type 1, type 2 errors are we expecting, and can we actually get this achievement? And note that you should really decide these things ahead of time before you even do the analysis. Because otherwise, if you do the analysis and you're like, oh, my p-value is I was thinking 0.01 was what I want for my p-value, but I'm getting 0.02. Okay, I'm going to change my p-value, so I have to get my alpha is 0.05. And so what the problem is when you start doing things like that, you can, you know, not on purpose, but kind of accidentally, what's it called? You can accidentally find, you know, significant values that are not actually making sense because you're basically trying to factor it in and just right. It's called p-hacking. There's a bunch of other things you can do, and we'll talk about that today too, right? So that's kind of like what comes from experiment. Even though we usually aren't the ones who are doing quote unquote the experiment, we're not the ones usually gathering the data from the field, from the real world, okay? And then of course we have our analysis, which ends up being our t-test, our statistical testing, usually sometimes A/B testing. We'll talk about that today. We'll mostly focus on t-tests because t-tests are very common, very kind of like simple to do, but no, there's other things you can do, for example, chi-squared test. There's other statistical analysis we can do, right? And then of course conclusions, and that's one of the biggest ones. I remember like when I was teaching science fair with middle schoolers, I always said your conclusions are one of the most important parts because everything else, you can talk about everything you've done and you can even like say, you know, how you did the experiment, but your conclusions need to say, after you do the analysis, how does that tie with the rest of your experiment? So if you get, for example, if you know your data is only like collected from first graders, you know, and you do your conclusion and you conclude that for the rest, this is true for all people in the whole world, well, obviously that's not true because you're only looking at first graders. And of course, that's a pretty extreme example. but you can see a little more subtleness to it. You can kind of think of like what things are limiting factors from your data, like where did the data come from? So those are things that you consider as you write your conclusion. Okay, so cool. Any questions about the scientific method in general? Cool. Yeah, so hopefully that's kind of review. The curriculum does go into a little more like, paragraph form, but I think that's pretty much going through. The big one probably is when we talk about like our experiment. And usually that's like saying how the data is collected and how you're going to proceed before you actually do your analysis. Okay, so a couple things to realize when we say making a good experiment. Again, making a good experiment likely means that you're probably not collecting it. You could be, depending on your situation. But on a lot of data scientists, you're not the one collecting that data from its raw form. Usually you are collecting some data that was already performed from an experiment. And you can think of anything as an experiment in that case, of whatever your data looks like. Okay. So a couple things, control groups. So if you guys have heard of control before, basically it's like, think like placebo for like the medical field. Basically it's the thing that doesn't change. It's like the thing that you're comparing it to. And then you have a control group and usually like an experimental group or experimental groups, and saying you're changing one thing from that control. So that way you have that, what's it called? That ability to make inference and say, oh, okay, are these correlated or not? So sometimes we don't have, when we have data in our studies, we don't have a good, like, they didn't perform a control group. And so you have to figure out saying, can I compare this with another set of data? Like maybe I can look at other data that has similar features, but they had some control over it. Or you can say, maybe you proceed forward, but you have to be aware that there wasn't a control group and be aware of that in your conclusions. So these are things that you have to keep in mind. Random trials, the gold standard is a random trial. You might have heard blind and double blind studies. Do you guys know what double blind studies are?
Isn't it like the people who are conducting the experiment don't even know what the result? Yeah, that's.
I think you. Yeah, so Matt's not sure either. You had the right idea. You were getting there. Basically, so you can think of like a single blind study. It's like we give you, let's say like the classics like medicine. Like we give you either placebo or the medicine. In a single blind, the experimentee, the subject, doesn't know which of those two things are. They don't know if they got the placebo or the medicine. In a double blind study, not only does the experimentee, the subject, not know which thing they have, but also the experimenter giving out the information doesn't know if it's the placebo or the medicine. And the reason why is because you might accidentally introduce extra bias. Basically, you're trying to control as many different factors you can. So for example, I don't know, like the classic is like, if you didn't have a double blind study for those kids, like, oh, people prefer Pepsi over Coke and it's done by Pepsi. And it's kind of like, it's like, well, did the experimenter go like, oh, have this soda, or like, some other factor in that sense where they knew this was the thing. Maybe they had something more subtle than that. But the point is that you can introduce extra bias by not having a double blind study. And this is really true for the medical field. If you read the research and like you're getting some information from some research and you see that those things are not put in place, random trials, control groups, double blind, then you should immediately kind of squint your eyes and be like, like, why wasn't this done? And what kind of conclusions can I draw before I even like get into the analysis? So things to keep in mind. Sometimes random trials are not done. For example, there's something called a representative sample, but random trials are usually the gold standard. Like we like to have a random set, but there's other methods to also getting the data. So just because it's not random doesn't necessarily mean that it's no good. So real quick, let me ask you guys. So do you think, so do you guys know how most medical tests are done? Like how they get their subjects? So like a lot of times they'll ask for volunteers for the subject. Does that make it a random trial?
Not really.
Yeah, if you think about that, right? You have volunteers. For example, the classic is like having college students come in for experiments and stuff like that, or a university. That ends up being a certain group of people. So something to keep in mind. Now, that doesn't mean your results are not valid. It's just something you have to kind of realize saying, well, where this data comes from might put in some bias that we hadn't accounted for. And it doesn't mean you can't get results from it, just always being aware of being like, well, just know that we might be limited in what we can actually say about it. Okay. Next couple things is sample size. Basically, the more people you have, the more subjects, the more data points you have, the easier you can be, the more confident you can feel that your analysis will be representative of the actual population. We kind of talked about it with the t-distribution. Basically, we're hoping that things are, when we get very large data size, the central limit theorem allows us to kind of focus in and say, oh, is this actually, sorry, like if we get a large sample, basically we can say, oh, this probably represents the population better, okay? Reproducibility, basically make sure the experiment's reproducible. If it's, these things are hard, especially with data like when like you observe something for like, let's say some tragic event or something like that, that, you know, very rare, something like that, that can be difficult, and trying to figure out what other data sets you can compare it with. So again, that should always be in your mind, saying, can this be reproducible, and making sure that the experiment description, the collection of data was actually described, because then you can actually use that same procedure and say, okay, what other, you know, studies or data sets can I find that follow that same procedure or close enough to that procedure that I can actually compare the two. Okay. Last thing is this, I have these good examples. One thing I really like watching is healthcare triage on YouTube. I don't know if you guys have seen this before. I like to describe it as like one of the most boring YouTube channels that to recommend to someone, because they talk about healthcare, which is, I think it's awesome. I think it's actually a great channel, but he really likes talking about the numbers and saying, you know, like, here's a meta-analysis. Well, this analysis said, you know, this research did this. And he says, you know, they found a relative difference of this, but that's a relative difference from 0.01% to 0.02%. Is that really twice the fact, you know, like, he kind of goes into this part, and I think he does a really great job in explaining parts, but he really does a good job. Like, I think if you want to see someone take some information, like medical stuff, he's not a data scientist, he's actually a healthcare physician, but taking some like information and seeing how that relates to like basically his conclusion, he does a really great job in doing that. And in my opinion, it doesn't really matter what he's saying in the sense of being like what he concludes, it's the way he's proceeding and essentially showing you the research of what happens, and does a good job on that. So I highly recommend checking out those videos. So cool. All right, any questions about anything about experiment design that I kind of went through? Cool. All right, so again, the best thing to do is just see what other good examples are, and then, you know, just being aware of like what things you're looking at and what kind of conclusions you can draw.